Hi there, and welcome to this short demonstration of the new Multi Boolean Union functionality that was added in Polygonica 3.1. So Multi Boolean Union is the idea that you can take a long list of different solids and union them together in one single operation. And in this demo I'm going to use the idea of lattice creation for additive manufacturing in order to demonstrate that. But really the focus is on the speed and flexibility and power of this new operation that can do many booleans in one go. So just to quickly explain the workflow used in this demo, I'm going to take a solid, in this case a sphere. I'll create an inwards offset, so that's a spherical inwards offset, this standard Polygonica offset functionality, and that creates a new internal surface. And later on, after I've created the lattice, I'm going to clip the lattice against that internal surface. And then I'm going to generate lattices using two slightly different workflows. The first makes use of Polygonica's existing fast polyline clipping. So that's the idea that you can pass a big array of polylines, thousands of polylines into your model, and it will clip against the polygon mesh really quickly. And also it will clip against the intersections of the polylines themselves. So it gives you a whole bunch of points where you can create, in this case I'm going to add spheres at each intersection point and add cylinders at the start and end of each lattice segment. So this gives you all the coordinates, really quickly gives you all the coordinates where you need to create the lattice beams and nodes. So that's one way of doing it. A second way I've used is simply to create a variety of, if you like, unit cubes, and then reproducing those unit cubes as instances. So we don't copy the geometry, we just instance the geometry in space to create a much bigger unit cube representing the lattice, and then use the Multi Boolean Union to union them all together in a single operation. And then we can work with that and clip that against the part. So here's the final parts of the operation. You clip that cuboid lattice against the internal offset surface that we created earlier. So that's a Boolean intersection operation. We then hollow the solid out by subtracting the offset surface. So that's a standard hollowing operation and Boolean subtraction. And then we join the lattice to the internal hollowed solid using a single part-part Boolean union operation. And you can see the result below. You've got a hollowed out solid with an internal gyroid lattice. If you want to ask us any questions, you can contact us through the form on the website. We also have LinkedIn pages for MachineWorks Limited and for MachineWorks, the software libraries, and also for Polygonica, the software libraries. So you're welcome to follow any of those, and we'd encourage you to do so. And we'll be notifying people of new videos and new releases and things like that through those pages. So please do follow them if you're interested in Polygonica, excuse me, or MachineWorks. So on to the demo. The first thing to say is that this graphical user interface I'm using, it's not an available product. We don't sell it. It's just an internal demonstration product. It's very old, written in MFC, etc. So Polygonica is a set of software libraries written in C that you can integrate inside your own software products or put inside your cloud architecture or on-premises pipeline, whatever. Okay, so on to the demo. First thing I'm going to do is just create a sphere, and then I'll go through the different workflows I explained in the presentation, creating 4 different types of lattice just to demonstrate each different workflow. So firstly, I'll create a polyline grid. Now that's actually a function that's been in Polygonica for a while, and it just basically does very fast polyline clipping, which is useful if you want to determine the coordinates of where you want to put beams and nodes and where they need to be clipped to the surface, etc. So here I've just created an 8x8 by 3 grid, but you can pass your own polylines into this and have them clip very fast. So just to give you an idea of that, I'll do 100. I won't do more than that simply because the graphics start to struggle, but you can see I've just done 100 instantaneously. So we can make use of that to create what I've called here a stretched grid. So let's just get that going. So I've called it stretched because it doesn't, it keeps the same number of cells, if you like, in X, Y, and Z. So if the bounding box is stretched, then the lattice grid itself will be stretched. And here you can see it created that in 1.35 seconds. So it's created a clipped lattice, which you can see here. If I zoom in, you can see Polygonica has created all these spheres and cylinders at the points where the lattice grid told it to. And then the Multi Boolean Union, they were all thrown in as a big bunch of solids into the Multi Boolean Union, and it's unioning them together into a single solid. And you can see on the right here that there's one shell in this scene. So there you go. And if I look at it inside the sphere, so we can see we've done a number of operations here. We've offset the sphere inside so that it's actually hollowed it out, and then we've clipped the lattice to the internals. You can see that quite nicely. So I'm going to do that same set of operations with different lattice creation techniques. So I've just undone that. Now I'll do a uniform grid with the same resolution. So in this case, rather than use the lattice clipping functionality, what I've done is just create a single cuboid cell of beams and nodes, and then repeated that 8 by 8 by 8 throughout the structure. And then those cells have all been thrown into the Multi Boolean Union, which has unioned them together. And then that's been clipped to the surface of the sphere. So that's taken 1.6 seconds. So a very similar sort of speed. And you can see there's the results. And again, if we look inside the sphere, you can see it's inside the sphere there. Again, undo that and add something a bit more challenging. Let's go for a diamond lattice. So this is the same principle in creating one small diamond cube and then repeating it in an 8 by 8 by 8 grid, unioning that all together, and then clipping, and that will create the clip lattice, and also unioning the clip lattice to the hollowed out sphere. So there's the results of that, and you can see there's a nice diamond structure. Obviously, some interesting artifacts there where it's just clipped the surface. But you can see that that's all been done. I mean, that took 9.5 seconds. So very quick, and there it is inside the sphere. And again, you can see this is one shell, so it's one single solid. And finally, I will try the tool solid. So let's just undo that. So I've not written any code to create a gyroid. I've just got a nice gyroid model here. So there's my little cuboid gyroid model, and I'm going to use the same principle, just repeat that 8 by 8 by 8. So tool and infill. Now this will take a little bit longer because obviously the tool itself, the gyroid, has a fair number of polygons in it. But you can see it's done the Multi Boolean in 5 seconds there, and it's clipped to the surface in 9 seconds. And now it's unioning it all together in 5 seconds. I think the whole thing is going to take about 20-25 seconds, something like that. 29 seconds. And it's loading up the clip lattice, checking it for errors, which does take a little bit of time on a solid of this size. And there it is. So that's the clipped version of the gyroid. It looks pretty funky, but then I guess gyroids do. And there it is inside the sphere as well. So I could just show those alongside each other. I'll just close the sphere and tile them up. And so those are the 4 different types of lattice generation I've just put into this demo. And it is demo code. I've just done this kind of in my spare time just to show you what you can do. The main thing is that you've got a bunch of Boolean operations that work really, really fast and are really, really robust, which is one of the real strengths of Polygonica. Okay, I'll close those down and move on to the next demo. So now I'm going to just try that with a slightly more complex model. So I'll just create a couple of different lattice types. So here's a standard 3D benchy. It's about 250,000 polygons. And let's try a diamond first of all. So diamond infill. It'll take a little bit longer because it's got more geometry to work with. So it's done that multi-union lattice beams and nodes in 5 seconds there. So it's taken 8 by 8 by 8 copies of the diamond shape and unioned them all together in 5 seconds. And then it's taken 12 seconds to clip that to the inner surface of the 3D benchy model, because there's quite a lot going on in this model. And then we'll see the results. So the whole thing took 29 seconds, including copying out the clip lattice. And it's just showing purple there are disconnected bits of lattice. So there's, the lattice density here isn't enough for the thin regions, but you've got a pretty nice view of the clip lattice there. And similarly, I can show you in 3D benchy itself. You can see there's the clip model, or there's the clip lattice inside the model. Again, there's one shell here, so it's one model. If I just section through that, let's turn that transparency off. Look from above, so we can just go up and down through the model. Let's fill the solid, so you can see we've offset the solid inwards as well. So it's all pretty quick, and there's the lattice inside it. Great. Okay, so I'm going to undo that and do the same, but with the gyroid this time. Load tool, gyroid. So I've loaded in the gyroid. This time you can see it's much smaller than the 3D benchy model. So there's no units in the files we're loading in here. So I just scale it to the bounding box when I come to generate the lattice. And tool, and I'll just do 6 units just to save a bit of time because it's a demo. So we're going to create 6 times 6 times 6, a cube of 6 times 6, 6 times 6 of that gyroid model. So it's doing a fair bit of work. The offsetting of the surface took 1.7 seconds. The multi-union operation of those 6 times 6 times 6 cubes took 12 seconds. And it's got to do the clipping to the inside surface, which is, as you can imagine, is a fairly complex Boolean operation. And that took 15 seconds, and then it's unioned the clipped version together in 4 seconds. So the whole lot's taken 42 seconds, which is pretty fast for a model of this type. And oops, sorry, there's the results. So you can see, again, you probably want a bit more of a density, but this is just for a demo, a bit higher density. You can see the letters in the base, so you can just about make out that the letters in the base have been imprinted in there. So that's a nice result. And again, if I make this transparent, you can see there's the gyroid inside. And I'll do a clip plane and turn off transparency, and then we can just zoom in a bit. And there we go. So a nice gyroid lattice infill through the whole of the part. Let's look at it on the side. There. Okay, so that's the end of my quick demonstration of the new Multi Boolean Union functionality. As always, if you want to get in touch, please go to the Polygonica website, polygonica.com, or you can contact us through LinkedIn. We'd encourage you to follow our various pages on LinkedIn. There's a Polygonica page dedicated to Polygonica, a MachineWorks page dedicated to the MachineWorks libraries, and also MachineWorks the company. So there's 3 possible pages on LinkedIn you can follow, and you're welcome to connect with us and ask us any questions or fire us questions through the website, and we'll do our best to answer you. Thanks very much for your time.